Newton's method of solving equations, page 349. They had 4 problems to do. Any questions you have? Once again, what I'm looking for in that, because your calculator does a lot of stuff for you, what I'm looking for in the solutions is you need to give me, when I give you f of x, you need to give me f prime at x. You need to give me that. You need to give me the initial guess x1, and then list your x2, x3, x4, x5, and so on down the line. Okay. So that's what I expect out of those problems using Newton's method. Any questions you have on solutions, how to deal with that? Once again, we set your calculator up nicely, hopefully set it up nicely, that you have stored in your x3, or I'm sorry, in your y3. You should have stored in there Newton's method of solving an equation. If you ever get into college and get into computer programming in college, and working through computer programming in college, this will be a very basic computer program that you'll have to write. It is Newton's method of solving equations. It will just, your steps, it will give you, your program will give you these values here as you go throughout. So once again, if you get into computer programming, you'll deal with Newton's method again in solving equations. Anything you need to go through with that? Hopefully you're keeping up with it. I get it. We are, for you seniors, you're 10 weeks away. We're 10 weeks away from being done here and getting completion. But you need to continue to push yourself through your academic responsibilities. You're 10 weeks away. I'm 10 weeks away also. I'm doing it. You guys can do it. You guys are seniors. I'm a senior citizen. We can do it. It's not a big deal. Today we're going to go through the last section in this chapter 4, and we start dealing with what is called the indefinite integral, or what is called the antiderivative. In mathematics, as you've been in my class a couple years now, you've heard the spiel, and you hear the speeches, and you hear all the ideologies of mathematics and the ideas of mathematics. In regards to mathematics, we do mathematical processes. We continually do mathematical processes in this class. We've learned how to go step by step to be able to solve mathematical things and use mathematical whatever, logs, exponents, anything, trig functions, the early transcendentals, or just multiplication, division. We've learned how to do mathematical concepts. But for every mathematical concept that we have done, and this is what allows students to be a math brain, is this is how their body and their brain works. Their brain works is they can set a set of processes and follow a recipe to solve a problem. And they know the step-by-step way of being able to solve a problem. Okay? But with that, for every problem that we solve, we have to also mathematically be able to unsolve that problem. For everything we do mathematically, there is a way of being able to undo this stuff mathematically. Well, what we have dealt with up until now in this class is we have dealt with limits, and we have dealt with oodles and oodles of noodles of derivatives until they're coming out our ears. And it almost sort of gags us in regards to how many derivatives we have dealt with. Well, derivatives is a mathematical process too. And with that mathematical process, we also have to be able to undo it. And that starts our next section of calculus. And if you follow the Calc series into the next level of Calc 2, Calc 3, Calc 2, all the things that have started coming out your ears with respect to derivatives, in this chapter, in this class, Calc 1, the antiderivatives and the integrals will be doing the exact same thing in Calc 2 for you. Okay? It will be coming out your ears in regards to deal with integrals and applications of integrals and antiderivatives. And all of our chapter 5 is an introduction into Calc 2 for you. Okay, so you get a good introduction to Calc 2, a good starting spot, push in the back into Calc 2. Well, if we take a look at the function f of x equals x squared plus 2x minus 5, and we look at the derivative, what would be our derivative to the function? Start you out nice and easy here. I have 3x squared plus 2x minus 5. I want you to take the derivative of that. Nick, what do you have? 6x plus 2. We have done a mathematical process going from a function to the derivative. We want to now deal with what is called the antiderivative, which is undoing the derivative when we were dealing with trig. We dealt with trig functions and inverse trig functions. Well, when we deal with derivatives, we don't do inverse derivatives. We do them antiderivatives, which is also called an indefinite integral. When we call it antiderivative, we could call this an indefinite integral. And once again, the idea of integration is a process that you will see throughout the entire Calc 2 world. What we want to be able to do is we want to be able to take our 6x plus 2 and take it back to what we had before, 3x squared plus 2x minus 5. We want to put this process into reverse. Well, to do this, we have to take a look at some notation. How do we symbolize that we're taking the antiderivative here? How do we symbolize that? Well, think about if you had the letter S. You have the letter S, and you're able to make it very elastic. And you grab the top part of the S and the bottom part of the S, and you stretched it out. You did some stretch Armstrongs with them. Okay? You took top S, bottom S, and stretched it out. What you'll come up with is well, here's our letter S. I'm going to stretch it downwards. I'm going to stretch it upwards. I'm going to get an elongated S. This here tells us that we're dealing with the antiderivative of a function. It's a stretched out S. So we're going to take the antiderivative of the 6x plus 2 But we also have to throw the idea into this with a differential. If you remember back to when we did differentials, y equals 3x squared plus 2x minus 5. Then we went dy dx is equal to 6x plus 2. Then our differential we multiplied by dx. We have 6x plus 2 dx. That was our differential that we did in the previous chapter. So we can make this a differential, we have to throw a dx at the end. What this dx tells us to do is this tells us that we are, once again, as we're taking the derivative of y with respect to x, it tells us what we use our derivative rules basically with, or to, in our function here. I go 3 times 2, subtract 1, 1 times 2, subtract 1. We do that all in regards to with respect to the value of x. So we're using all of our derivatives rules to the x variable. Well, this, throwing the dx at the end with respect to the differential, tells us we're going to take the antiderivative and we're going to apply all these rules to the x variable. So what we're left with is the antiderivative of 6x plus 2 dx. And we want to be able to go back to where we started from. Well, let's take a look and let's dissect once again what we did before. We had f of x is equal to 3x squared plus 2x minus 5. If we go back to our, we now can go through this quite easily in our brain, hopefully. We are hopefully able to click 6x plus 2 out of this real quick. Now I'm going to slow your brain down again because we have to remember the process is what we did to get to this point. When we took our derivative, we went 3 and we bring the 2 out front, and then we went x to the 2 minus 1 power. So we multiplied our coefficient by our exponent and subtracted 1 from the coefficient, or exponent. Plus 2 times 1 times x to the 1 minus 1 power. This is putting our process in our process, and I'm slowing your brain down again to show you what we did to get to this point. Because what we want to do is we want to take this and get back to this up here. Okay? We want to take this here and get back to what we originally started with. Because we want to be able to have the undoing process. Whatever we do, we want to be able to undo in the math world. Well, to get this 6, we had the 3 times 2, and we subtracted 1 from our exponent. Well, we're going to put this process now into reverse, which means we're going to do our process a little bit backwards. Before we dealt with exponents of the coefficient, subtract 1 from the exponent. We're going to look at the exponent first here. What we did to get to this point is we subtracted 1 to get to this point. Well, to undo the subtraction 1, what would we have to do with our exponent? Add 1. So we're going to add 1 to our exponent. So we have 1 plus 1, which is a value of 2. So we're going to get an x squared here. What we did to get this value of 6, we multiplied 3 times the 2. Well, how did we get the 2? Well, we took our exponent of 2 and multiplied by the 3 to get the value of 6. Now we want to get back to the value of 3. So we now have this new exponent here, which is the value of 2. And if we take a look at our coefficient of 6, we could take our 6 that we had there and divide by this new exponent of 2. It is putting your mind in reverse. Before we took exponent, multiplied to the exponent, or to the coefficient, subtract 1 from the exponent. Now we're going to go to add 1 to the exponent first, and then divide by our new exponent, which will take us back to 3x squared, which is what we want to get here. We have 2 times x to the 0th power. But there's no x there, it's x to the 0th power. So we want to follow the same method of madness. So we're going to take our 0 and add 1 to it. So we have our new coefficient of 1, or exponent of 1. This new exponent of 1, we're going to divide our coefficient by this new exponent of 1. So what we're left with here is 3x squared plus our 2x, which gives us our first part here. Now the problem we run into when dealing with antiderivatives is using antiderivatives to go back and undoing the idea of a derivative is we are not going to just make the constant reappear. We have to have other conditions to make the other, or the constant to make it appear. And we don't have those conditions right now. Eventually we'll be able to solve for that constant. But we don't have conditions to be able to solve for the constant. So the only thing that we can do here is put a plus c in. And what we're saying when we put this plus c in there, there's some constant. Not quite sure what it is. It could be any number. We're just going to put a plus c in there for right now. Which allows us now to go back to close to what we originally started from. Once again, we need to have an initial condition to be able to get the c value to the function. And we don't have that. But it allows us to get us the variables and work with the variables and get the variables and exponents to where we need to be. The most difficult thing for students is we have dealt with derivatives for a long time here. And you're so stuck up here in your brain how to deal with derivatives. And to get yourself out of the derivative mode and go into the antiderivative world. And put your brain into process in the reverse. What we deal with respect to the antiderivatives, you deal with exponent first. Then your coefficient. Okay, that's the mentality that you have to have when dealing with the antiderivatives. Exponent first, then the coefficient. Where what we dealt with in derivatives, we dealt with basically the coefficient first, and then we subtracted 1 from the exponent. We're going to dealing with the exponent first, adding 1, and then working with the coefficient. So in general, we could get a antiderivative formula or rule where our derivative rule with respect to exponents was a times n x to the n minus 1 power. Okay, this is what we worked out with the derivative. And that's the process we work with respect to derivative. We now have an antiderivative rule, where if I still have my antiderivative of ax to the nth, this is equal to 1 over, or I should put an a here. Should be an a. A divided by n plus 1 times x to the n plus 1 plus c. My suggestion to you, and this is what I see a lot on students' papers as you go forward and go into the antiderivative world. I give you this, I see this a lot. I see a plus 1 there, so that reminds students that I have to add 1, add 1, add 1. And I work with that first. If we look at a constant, the antiderivative of a constant, okay, once again, this is the antiderivative of a constant, x to the 0th power, dx. Add our 1. So we have x to the first power, and we divide c by this value 1. So we have c times x to the first power. So when you have a constant there, when you're taking the antiderivative of a constant, it's just going to be the constant x to the first power. Because once again, we're just following the rule of adding, we have a constant times x to the 0th power, we add 1 to the 0, which is 1, and we divide our constant by the 1. And we have some other constant we add to it. We can use any letter we want there. So looking at a function, 12x squared plus 8x minus 5 dx. I want to find the antiderivative. Once again, my suggestion to you, always throw a plus 1 there. Work with your exponent first. So we have x to the 3rd. And this new exponent, you divide your coefficient by. So this new exponent that we have, this value here goes on the bottom. So we have x to the 2nd here. This new exponent comes down on the bottom. The derivative of a constant will be the constant times x. So we have minus 5x. And then don't forget your plus c. Okay, this is a common thing that is forgotten. So we're left with 4x cubed plus 4x squared minus 5x plus c as your antiderivative. Well, what if we had 10 over x cubed? I need to get into the form of a times x to the nth power. So how can we rewrite 10 over x cubed? What can we do with the x cubed on the bottom? Throw it up top and make it a what? Negative. So we have the antiderivative of 10 x to the negative 3rd dx. So add your 1. Add your 1. Get your new exponent. Divide your coefficient by your new exponent. Slow your brain down. Don't try to do too many things at once here. Remember, what's our new exponent going to be? -2. What's our new coefficient going to be? I divide by my new exponent, so I have 10 divided by -2, -5. And then we have, once again, don't forget your plus c. And then you need to get rid of your negative exponents. So we have -5 over x squared plus c. Sometimes you just have to think back to, what do I have to take the derivative of to get what I'm taking the antiderivative of? What did I take the derivative of to get the sine of x? Okay, so what we have to remember back to, derivative of sine was cosine. The derivative of cosine was negative sine. Derivative of sine was cosine. Derivative of cosine was negative sine. So what do you think the antiderivative would be of just the sine of x? Negative cosine, that's correct, very good. Plus c. What would be the antiderivative of cosine of x? Sine of x. Okay, and this is once again a tough thing for students to look at and remember, because we're so stuck up in our brain. Derivative of sine was cosine, derivative of cosine was negative sine. Now it's opposite. The derivative of sine is negative cosine, or the antiderivative of sine is negative cosine. Antiderivative of cosine is back to sine. Secant squared. What do we take the derivative of to get secant squared? Tangent, very good. Tangent of x plus c. Take the derivative of tangent, came down to secant squared. So the antiderivative of secant squared would be tangent. Let's see here, square root of x. X to the 1/2 power would be your antiderivative. Once again, I will ask you to simplify radicals. I won't necessarily make you rationalize, but I'll get you maybe some ugly things to work with. I will ask you to simplify them though. take 1/2 plus 1, you get 3/2. My coefficient is a value of 1. So we're going to have x of 3/2. Then we have 1 divided by this 3/2 plus 3. Take my coefficient, divide by my new exponent. So if I have 1 divided by 3/2, this simplifies down to what? 2/3. X of 3/2 will simplify down to x square root of x plus c. We have x of 1/1/2, which is x to the first times x to the 1/2. So we have x square root of x. Well, what happens if we have the antiderivative of x to the negative first dx, and I try to add 1 to this, and I divide my coefficient by my new exponent? We have an issue. But if we go back to the mentality of what did we take the derivative of to get 1 over x? Anybody remember? ln of x. Now what we're going to do with this, because eventually we'll throw some numbers in with this, and we're going to throw that as an absolute value. Because we need to make sure we stay positive with this. Once again, taking a lot of things that we did first half of the year, derivative-wise, and putting our brain into reverse. Which allows us now to look at the idea of what is called differential equations. Differential equations allows us to be able to, once again, get back to original functions and also be able to solve for that c value. And a way of solving in differential equations is an entire course in college. We'll touch on it here, but you'll get into what is called differential equations in college, which is Calc 1, we've dealt with. Calc 2, a lot of integrals. Calc 3 is a lot of applications of both Calc 1 and Calc 2. Calc 4 is what is called, in some colleges, they'll call that differential equations. Some colleges will call it Calc 4. They'll call an entire course differential equations. If we look at the value or the equation, dy dx is equal to x over y, we want to ultimately get back to y equals. What is y equals? What could y equal here? Well, we have a differential equal to two different variables. When we dealt with this in derivatives, we've dealt with this sort of like an implicit differentiation. We can separate our variables, which means we want to get our y's together and our x's together. Well, if we multiply both sides by y and both sides by dx, what we're left with is y dy is equal to x dx. What we have done is we have separated our variables into two sides. We put the y's on one side, put the x's on the other. To get rid of our differentials, how do we get rid of our differentials? Is by looking at the antiderivatives. Just like we took the derivative of both sides, we can antiderivative to get rid of our differentials. This tells me I want to apply my rules to the y variable. This tells me I want to apply my rules to the x variable. My differential will tell me that. Our exponents are 1. We add our 1, we add our 1. We're left with 1/2 y squared plus c is equal to 1/2 x squared plus some other constant d. We don't know what these numbers are, but we just have to add them in. Now we can collect both of our variables on one side of the equal sign and our constant on the other. And you can use any letters you want to use here. You could use, if you wanted to, if I subtract d from both sides, I have a constant minus a constant, I'm still going to get a constant. So I can use any letter I want. I could use a C in here, I could use an A, I could use a B. It does not matter what I use. I could use a Z if I want to. I just have to symbolize with a capital letter, it just gives me a constant. So this C and this D, they could be the same, they could be different, but what we're left with is a relationship between X and Y. If I wanted to, once again, there's all kinds of things that you could do in regard to this. I can multiply both sides by 2. So we now have 2c is equal to x squared minus y squared. Well, if I take a constant and multiply by 2, I'm still going to get another constant. And this is sometimes tough for students to look at also, because you're just saying, well, I have 2 times c, I can still call that c. I can still call that a constant. So we have x squared minus y squared is equal to some constant c. Very quickly, the last one here. If we separate our variables, dy is equal to 3x squared plus 6x minus 7 dx. If we take the antiderivative, of dy will just give us y is equal to x cubed plus 3x squared minus 7x plus c. Dealing with our antiderivative, we are given an initial condition where if x is equal to 1, y is equal to 7, which allows us to solve for this value of c. So we're left with 7 equals 1 plus 3 minus 7 plus c. And then we can solve for the c value by adding 7 and subtracting 4. C equals a value of 10. We'll work with more on Monday at page 355, 127 the odds. Have a good weekend, everybody. I will try. Like huh? We all are, huh? Rough week.
There's a way to do it on the bigger graph and calculator, but I found the video ones. So I'll let you